Hi everyone, so today I have a video on acid-base review for midterm 1 for Chem 1 AA3. So I just have a few practice problems to go over which are heavily inspired by the past 3 years of midterm 1s. So hopefully this will be accurate. So let's start with the first question. What is the pH after mixing 200 mils of 0.15 molar HCl with 300 mils of 0.1 molar NH3? And we have the Kb value here. So this is a pretty standard problem. So first I'm going to write out the chemical equation. So HCl plus NH3, and this is going to give NH4 plus Cl minus. So what I like to do is write out the information that we have underneath the equation. So for HCl we have 200 milliliters, which is 0.2 liters, and 0.15 molars, and for NH3 we have 0.3 liters and 0.1 molars. So what I'm going to do now is calculate the moles. So N, the moles, is concentration times volume. So if I want to find how many moles there are, this is 0.2 times 0.15, and this will give me 0.03 moles. And I can do the same for ammonia. So 0.3 times 0.1, so 0.03 moles. So we have the same amount of moles on both sides. And because all of my coefficients are 1, I know that the moles of ammonium are also going to be 0.03 moles. If you had a different number of moles, you would just use whatever the limiting reagent was, so the smallest amount of moles. Now I also know the volume because I know that I had 0.2 and 0.3 liters. So now my volume of NH4 plus is just going to be 0.2 plus 0.3, which is 0.5 liters. Now if I know the moles and I know the volume, I can find concentration, which is 0.03 divided by 0.5, which will give me 0.06 molars. So now this NH4 plus is going to react with water, and it's going to form hydronium and ammonia. And I know that the concentration of this is 0.06. And now this is essentially going to turn into an ice table. So I will subtract a certain amount of X, and then I'm going to add a certain amount of X on the product side. So what I have is 0.06 minus X, and then X. Now something that we have to convert is we're given a Kb value, but as you can see, we're producing hydronium. So in order for us to calculate, we need to find the Ka value. So Ka is the Kw of water, which is 1 times 10 to the negative 14 over the Kb value, 1.8 times 10 to the negative 5, and this will give me the Ka value. Now before I move on with my calculation, I want to check if this follows the small x approximation. So what that is if the K value times 100 is less than the initial concentration, then X is small. So if I multiply this by 100, I'll get 5.56 times 10 to the negative 8, which is much smaller than my initial concentration of 0.06. So I know that X is small. So now I can use my Ka expression to find what X is. And because X is small, I can ignore this X over here and simply multiply 0.06 over to this side. So if you calculate this, X will be 5.77 times 10 to the negative 6. And we know that X is over here, and that's our equilibrium concentration of hydronium. We can use X to find the pH, so the pH is just going to be negative log of X, which will give you 5.24, which is the closest to this number. This is actually the correct answer. The options were just slightly off. So now question 2, what is the pH of a solution containing 0.4 molars of acetate and acetic acid and 0.1 molars of acetate? And we're given the Ka value. So what I'm noticing first is that this is their conjugates. So I know that this is going to be a buffer solution, so I can use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is pH equals pKa plus log of the conjugate base, which in this case is CH3COO minus, over the acid. So what I want to find is pH, and I need to find out what pKa is in order to calculate. So what I'll do is I'll use this Ka value. Remember that pKa equals negative log of Ka. So negative log of this value is going to give me 4.74. And now I can plug my values into the equation. So 4.74 plus log of the base, so 0.1 over 0.4. And if you calculate this, you'll get 4.14. So option A. Next, question 3. A 0.25 molar weak acid has a measured pH of 3.40. What is the percent ionization? So the pH basically tells us, well, it's derived from the concentration of hydronium. So I have a weak acid here, and if I mix it with water, this is just your standard acid equation, you will get hydronium produced and then the conjugate base. And then the pH is derived from the concentration of this hydronium. So what I'll do is the concentration of hydronium is just 10 to the negative 3.40. And this will give me 3.98 times 10 to the negative 4. And that is how much it ionized. So this is the concentration after ionization, and this was the original concentration. So if I want to find percent ionization, I simply take the concentration of hydronium over the original concentration and multiply it by 100. And this will give me 0.16%. Next, which solution will have the highest pH? So we're given the Ka values of 2 of our species. So let's first identify what each of our options are. So I have hydrofluoric acid. This is a weak acid. Then I have NaF. So NaF is a salt which includes the fluoride ion, which is the conjugate base of hydrofluoric acid. Okay, moving on. So I have HNO2. This is also a weak acid. And then I have NaNO2, which is a salt, which includes NO2 minus, which is the conjugate base of HNO2 because it just lost a hydrogen. So which one has the highest pH? We know that it has to be one of these two bases that have the highest pH. But which one is it? Well, we have to look at the Ka values. So Ka, remember, is the concentration of products over reactants. So if I have a higher Ka value, what does that mean? It means that the acid dissociated more into the products, which means it will have a lower pH. And therefore, if I want to find the solution that has the highest pH, I need to pick whichever one has a lower Ka value. And the lower Ka value is the one for HNO2, which corresponds to NaNO2 for the conjugate base. So we're going to pick option D. Hopefully that one made sense. Next, a buffer is prepared by adding sodium hydroxide to 1 liter of 0.2 molar NH4Cl until the pH reaches 9.25. How many moles of NaOH are required? So first I'm going to write out the chemical equation. So NaOH is mixing with NH4Cl, and we are producing NaCl, our salt. We know that we have to produce some NH3, and then what's left over, we make H2O. And then this NH3 is going to react with water to produce NH4 plus and OH minus. So they tell me that I have 0.2 molars and 1 liter. So I know that I have 0.2 moles. I'm just doing the same thing, multiplying concentration by volume. So because I found out that I have 0.2 moles of NH4Cl, that means I will also have 0.2 moles of NH4 plus over here. And I can make a new ice table now. So I have 0 amounts of NH3 over here, and I have 0.2 moles, and then it's asking for how many moles of NaOH are required, so I added X amount of OH minus, which is going to completely react because we're asking for the minimum amount, right? So it's all going to be minus X, so minus X, and then plus X on this side. So now I'll use my Henderson-Hasselbalch equation because I'm recognizing that this is a buffer because we have the conjugate species together in a solution. So what I need is I will take the Kb and convert it into Ka. So 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5. And this will give me 5.56 times 10 to the negative 10. And then find pKa, which is negative log of the Ka, which is 9.26. So now using the Henderson-Hasselbalch equation, so we know that it's pH equals pKa plus log of the base concentration over the acid. So I know my pH is 9.25. My pKa is 9.26 plus log, and then I'll have X over 0.2 minus X, and then just using simple algebra, I'll solve for X. So negative 0.01 equals log X over 0.2 minus X. And then remember that this is 10 to the power of this value to get rid of the log. So 0.977 equals X over 0.2 minus X. Multiply this over, you'll get 0.195 minus 0.977x equals X. And we'll find that X is 0.099 moles or 0.10 moles. And remember that X over here is the amount of NaOH that was added. So we know that the answer is C. What is the pH of a 0.1 molar NaCN solution? So let's write out our chemical equation once again. So this is a salt, so it's going to dissociate into its constituent ions. So Na plus and Cn minus. Remember that this is a spectator ion. And then our Cn minus will go on to react with water and produce HCN plus OH minus. So it told us that we had 0.1 molars of NaCN solution. So this was 0.1, and then this will also be 0.1. So I have this, and now I'll simply use the same ice table as before. So this dissociates. So minus X, and then these were 0, and then plus x. And I'll use the Ka value. So first I need to find Kb, which is 1.613 times 10 to the minus 5. And let's check if this follows a small x approximation. So if you multiply this by 100, you will see that it is much less than 0.1. So x is small. So this will equal x squared over 0.1 minus x. You can ignore that x and then find x to be 1.27 times 10 to the negative 3. And remember that this is the concentration of OH minus ions. So I will find the POH, which is 2.9, just taking the negative log of this number. And then the pH is 14 minus 2.9, which will be 11.1. Next, which buffer can neutralize the largest amount of added HCl without a large pH change? So the buffer that can neutralize the largest amount will be the buffer solution that has the most amount of moles. So let's go ahead and calculate how many moles are in each of the options. So remember that N equals C times V. So then this one is 1 times 0.1. So I have 0.1 moles. This will be 1 times 1, so 1.0 moles. This one is same as the first one, so also 0.1 moles. And this will be 0.5. So which one has the largest amount of moles? It's option B, and that's going to be the one that can neutralize the largest amount of HCl. Next, we have a theory question. At the half equivalence point of a titration of a weak acid with a strong base, which statement is true? So pH is not equal to 7. So at the half equivalence point, this is said in our notes, the concentration of the acid will be equal to concentration of the base. And by the Henderson-Hasselbalch equation, pH equals pKa plus log of the base over acid. So if these two are equal, then it's just going to be 1. And we know that log of 1 is 0. So that tells us that the pH equals pKa, which is option C. Next, a buffer solution contains 0.3 moles of an acid and 0.3 moles of the conjugate base. If we add 0.1 moles of HCl, what is the new ratio? So once again, I'm going to write out my equation. So because I'm adding a strong acid, this is going to react with the strongest base in the solution, which is A minus. So it's A minus plus HCl. This will produce HA plus Cl minus. And I had 0.3 moles of this before, and I added 0.1 moles of HCl. So this HCl reacts with the A minus, and it's going to reduce that amount and turn it into the acid. So if I added 0.1 moles, this is going to be subtracted by 0.1 moles. So the new amount of the base will be 0.2 moles. And then 0.1 moles of additional acid was produced. So then my new A minus to HA ratio is 0.2 moles over the original amount that I had plus this new amount that was produced when HCl was added. And this gives a ratio of 0.5. Last question, which pair of solutions of equal volumes will form a buffer? This is a very common question. So let's go through each of our answers. So let's look at option A. I have a strong acid HCl reacting with a salt. This will not produce a buffer. any strong like acid or base mixed with a salt is not going to produce a buffer because we want to have excess weak acid or base. So option B, I have 0.2 molar NH3, which is a weak base, plus 0.1 molar of HCl, a strong acid. So because they're of equal volumes, I know that there's going to be some excess NH3 that's left over because it has a higher concentration and the volumes are equal. So this NH3 will consume all of the HCl, so I have excess of this, and then this will react with the next strongest acid, which will be water, and produce NH4 plus OH minus, and then I have conjugates together in a solution, which will produce a buffer. So we know that our answer is B, but let's go over the other options. So here I have a strong base, NaOH, plus my weak base, ammonia. So two bases together will not form a buffer. And for option D, this is the same as option A. I have a strong acid, and then this is a neutral salt. So strong acid plus salt does not form a buffer. So we're left with option B. So that's the end of the video. I hope you found this helpful, and good luck on the test. Make sure to share this video with all of your friends, and I hope you guys found it helpful.